Okay, in the Schoology course, in Unit 5, which is the current unit, there's a folder that says week of 12/7 to 12/11. That's our current week, and there's the plan for the week. I just need to update a couple more things. But every day, make sure you log in all your classes, log in on time. It's 8:30 for this class. Today, we're going to do some stuff about writing formulas and names for basic ionic compounds. And really, Tuesday and Wednesday, much of the rest of this week is going to be about writing names and formulas for chemical compounds, so that from now on, whenever you see a chemical formula, you can just name it, or whenever you hear the name of a compound, you know what the formula is going to come out to be. And so there's a PowerPoint with some notes, which I'm going to go over very quickly, but really it's for most students or people who miss it. And then we're going to do some examples of, I'll show you how to write formulas and names for ionic compounds. And then there's a practice that you can do, writing and naming ionic compounds problems for practice. And I'll stay for the rest of the period too. So these are the notes I'm about to go over. And then here, binary compound nomenclature practice. So here's what nomenclature means. That's a word that's kind of a technical word, or a word that's used within certain fields. Nomen means name. Let's see, I gotta let a couple people in. So nomen means name, and clature is a method. So nomenclature means a method for naming. Whenever we talk about a nomenclature, it's the method or the system for giving something names. And in different kinds of fields, there are different methods for nomenclature. So like, for instance, in anatomy, there are systems and methods for naming body parts and body systems and stuff. In biology, you know that there are different nomenclature methods. So like, for instance, like sugars end with ace, and or end with ose, and like enzymes end with ace. And in chemistry, we have different ways of naming things with different systems. So what you'll see is ionic compounds usually end with ide or IDE. So if you know little tricks about the way in which things are named, or what roots of words mean, you can come up with an understanding of things that you haven't heard before. This is the writing and naming ionic compound practice. I'm going to post tomorrow some problems that will be an assignment, and they'll be listed as an assignment, but this is just practice for naming basic ionic compounds. All right, so that's that. Let me switch to a different screen here. Yep, that looks okay. So the PowerPoint says ionic compounds. These are the notes for that ionic compound thing. Let's see if this will work. There we go. Okay, so you know about ionic compounds. They're compounds that are made from elements on the left-hand side of the periodic table, coupled with elements from the right-hand side of the periodic table. It's a cation and an anion together make a compound that forms a crystal, and generically we call those salts. So that's the basics of ionic compounds. Every chemical formula always tells you which elements are present and how many of them are present. And it works a little bit differently with ionic compounds and covalent compounds. Since we're dealing with ionic compounds, these ionic compounds, it really refers to a ratio of the numbers of individual atoms that make up the crystal. So for instance, there's an example here. It says CaSO4. Every time you have an element, every symbol for every element has a capital letter, and then there may be another lowercase letter. So for instance, calcium is Ca, but there is also an element, carbon, which is just a C. So every time you see a capital letter in a compound, every capital letter is a new element. And then the subscripts, which are numbers that are written below and to the right of the individual element symbol, tells you how many of that atom are present in the compound. So for instance, and this is a kind of a complex one, it says CaSO4. That has one calcium, because there's no subscript after it. There's just a single calcium atom. There's one sulfur atom, and then there are 4 oxygen atoms. The 4 after the O refers only to the O. So that compound has 1 calcium, 1 sulfur, and 4 oxygens. For ionic compounds, those ratios are always the lowest ratio you could possibly have. So for instance, if you end up writing a formula for that CaS, which would be calcium sulfide, and you find that it looks like it's Ca2S2, for ionic compounds are always written as the lowest ratio. What I mean by that is because 2 and 2 are both divisible by 2, the ratio of calcium to sulfur is 1:1, or just CaS. You'll see what I mean by that in just a couple minutes. In the end, every ionic compound is neutral. So what that means is you must have as much positive charge as you have negative charge. You can't have any more positive charge than negative charge, or any more negative charge than positive charge. The total amount of charge must be 0. We find that pretty much everything in this universe is neutrally charged, unless you do work to separate charge from one place to the other, like in the examples of an individual ion. But the compounds themselves, they turn out to be neutral. So these are guiding principles for writing names and formulas. And the easiest way to see how this all works is just by a practical example, which we'll do in just a second. So you know on the periodic table that the charge is dependent upon, the charge for an atom or charge for an ion is dependent upon which column of the periodic table the element lies in. So all the alkali metals, which is the first column of the periodic table, they begin with hydrogen. They all have a charge of 1+. The next column of the periodic table, which actually begins with beryllium, those all have a charge of 2+. The transition metals, which are the metals in the D block, and they go from the scandium group through the zinc group, their charges vary. And I'll show you how to deal with writing ionic compounds, names and formulas for transition metals. But we're going to skip those for today. In the boron group, which is group 15 on the periodic table, or group 13 on the periodic table, they have a charge of +3. The carbon group doesn't typically form ionic compounds at all, but it would have a charge of +or-4. We're not going to have any examples with +or-4. The nitrogen group, those then are negative, so -3. The oxygen group, -2. Those are sometimes called the chalcogens. And the 17th column in the periodic table, all the way beginning with fluorine, those are the halogens. They have a charge of -1. So you can keep this chart in mind, where you have charges from +1, +1, +2, +3, and then going from, well, the charge for noble gases is 0, and then going from right to left, it's -1, -2, -3. So those are the ways that you figure out what charge atoms as ions have on the periodic table. There's 2 methods for writing formulas. And here's one example. So we'll use calcium and oxygen for an example. And if you have a periodic table handy, that can be useful. Here, let me just switch to, I can bring up a periodic table, I guess. Do this periodic table. Find a good one. Here's a good one. Okay, so if we're looking for a compound that's formed between calcium and oxygen, so calcium is right here on the periodic table, and calcium has a charge of 2+, or +2. It's in the second column of the periodic table. And then oxygen, well, that's right over here. Hold on, let me get rid of this from this other screen so I can see what I'm doing. All right, so oxygen's right here on the periodic table, and that has a charge of 2- whenever it's an ion. So we're trying to form a compound that has calcium, which is 2+, and oxygen right here, which is 2-. So let me switch back to this thing. The 2 different methods include one of them to look at what we call balancing the charges. In this case, calcium has a charge of 2+, and oxygen has a charge of 2-. So if these 2 ions get together, because they have equal charge, there's a charge of 2 plus and a charge of 2 minus. 2 plus and 2 minus gives you an overall or a net charge of just 0. Their charges will cancel out. So you only need them to be in a ratio of 1 to 1. So the compound that's formed between calcium and oxygen has a formula, CaO. The ratio is just 1 to 1. Another method that people use is what's called the cross-down method or the crossover method. And that's to look at the charges that each of the atoms as ions have. And whatever the charge is for the calcium, that's how many oxygens you're going to need. Whatever the charge for the oxygen is, that's how many calciums you're going to need. So it looks like with this method that you'd put a 2 after the oxygen and a 2 after the calcium, which is sort of correct in the sense that for every 2 calciums, there's going to be 2 oxygens, except for ionic compounds, we always write them in the lowest whole number ratio. So instead of it being Ca2O2, you could just write it as CaO. Writing calcium oxide as Ca2O2 is not acceptable. It's only acceptable for them to be in the lowest whole number ratio. So if you want to do this cross-down method, that works fine. But if you end up with a ratio of 2 to 2, or maybe it's 4 to 2, 2 and 2 is the most common thing that you would see. You would divide these each by 2 to just get calcium oxide, just CaO. So those are the 2 major methods, and I'll show you with practical examples the way in which each of those go. So for instance, if you have magnesium and chlorine, so if you have a periodic table handy, you can take a look at that. We'll go back to this periodic table. Magnesium and chlorine. So magnesium is right here. That's in the second group of the periodic table. It's got a charge of 2 plus. And chlorine is a halogen, and that has a charge of 1 minus. So we have magnesium with a charge of 2 plus, and chlorine with a charge of 1 minus. And the 2 different methods are to consider what the charges each have to be. Well, if magnesium has a charge of 2 and chlorine has a charge of 1, in order for that to be a neutral compound, you're going to have 2 chlorines to go with every 1 magnesium. 2 chlorines, each with a charge of -1, would give you a charge of -2. And magnesium with a charge of 2 plus then would balance out the 2 chlorines, each with a charge of 1 minus. But the other method is that cross-down method, where if you have a charge of 2 for the magnesium, that's how many chlorines you would need. And whatever the charge for the chlorine is, that's how many magnesiums you would need. So whenever the compound magnesium chloride forms from magnesium and chloride ions, for every magnesium, there have to be 2 chlorines, and the formula is MgCl2. In the case of the aluminum and oxygen, here, maybe this will be just a little bit quicker. You can just drag this down. That's good. So for magnesium and oxygen, magnesium is right here on the periodic table, is a charge of 2 plus. Oxygen's right here on the periodic table, has a charge of 2 minus. So when you consider each of those, oh, I'm sorry, we're doing aluminum and oxygen, not magnesium. Okay, so aluminum and oxygen, sorry about that. Aluminum is right here. Aluminum is in the 13th group of the periodic table. It has a charge of 3 plus. Everything in this as an ion would have a charge of 3 plus. And oxygen is right here, has a charge of 2 minus. So you have 3 plus and 2 minus. Really what you're looking for is the least common multiple of 2 and 3, which turns out to be 6. So it turns out that in terms of charges, if you have 2 aluminums, each with a charge of 3, that would have a total charge of 6 plus. And then if you had 3 oxygens with a charge of 2 minus, 3 times 2 also gives you 6. And 2 aluminums and 3 oxygens overall would have a neutral charge, or 2 aluminums each with a charge of 3 would give you a charge of 6 plus. 3 oxygens each with a charge of 2 minus would give you a charge of 6 minus. And you would end up with a neutral compound. But that cross-down method might be useful to see if this is the charge for aluminum, 3 plus, then you need 3 oxygens. And similarly, if oxygen has a charge of 2 minus, then the number of aluminums you need is 2. So the compound that forms between aluminum and oxygen has the formula Al2O3, and that is the least common, or that can't be simplified any further. 2 and 3 are each divisible by, all kinds of different things, but nothing to give you any kind of integers. So the compound that forms is an ionic compound between aluminum and oxygen, called aluminum oxide, has the formula Al2O3. And then here's the rule for naming. I've said it a bunch of times now with the different compounds. It's quite simple. The two compounds, the first is a metal and the second one is a nonmetal. The metal comes first. It's the thing on the left-hand side of the periodic table, and you don't change its name. The nonmetal, that's the anion, which comes from the right-hand side of the periodic table. Its name changes to end with the suffix "ide." So you change the end of the element from, instead of like, calcium or CaI2 is Ca is calcium. That's the name on the periodic table. And I is iodine or iodine, but you don't make it say calcium iodine. Instead, it's calcium iodide. You just change the name to end with "ide." Same with magnesium and oxygen. The magnesium and oxygen compound is then called magnesium oxide. And sodium and sulfur, that compound together is called sodium sulfide. So you just change the name of the anion to end with "ide." But that's also part of the nomenclature trick, is that anytime you see a compound that ends with "ide," it's typically an ionic compound that is a single salt. So if it's a metal and then ends with "ide," it's an ionic compound as compared to like a covalent compound. All right, so if you want to, or you should follow along, if you go to the folder for the week, there's this PDF file that says Binary Compound Nomenclature Practice. And the binary compound nomenclature practice has two parts to it. The first part have names of compounds, and we want to write the formula. And the second part has formulas, and we want to write the names. So this is the practice that I want to do with you, so that you can see how names and formulas for ionic compounds are written. So there's 10 names, we're going to write 10 formulas, and then there are 10 formulas, and we're going to write 10 names. And you need to be able to do this quickly and efficiently. It's a very important basic concept to be able to do in chemistry. So this PowerPoint, the ionic compounds notes, that's in the chapter 5 folder if you need to refer to it. Don't need to save that. But here is, I guess, yeah, the names are first on the page. So at the top of the page for that practice, and this is going to be recorded and put on the YouTube channel, and I will link to it in our plan for the week, in probably just like an hour or so for you to review. So we want to write formulas for these compounds. And let's see, the first one here is sodium bromide. So the bromide must come from some kind of element, and that element happens to be bromine, which is pretty easy to figure out. Do this. So this comes from bromine. If you're not sure, most elements on the periodic table end with "ene," or for the halogens, sometimes they end with "n" or "us" or "eum" or something like that. But the trick is to look at the beginning of it. The beginning won't ever be confused with anything. So brome, chlor, sulf, ox, phos, nite, iode, fluor, nite, and ox. These are the beginnings of element names that appear as anions toward the right-hand side of the periodic table. So anyway, sodium bromide. Where'd my mouse go? Here we go. Just pull this down. So we got sodium bromide. I need sodium, which has a charge of 1+, and bromide is from bromine, which has a charge of 1-. So I just need to consider a compound that's made of sodium, and sodium is Na, 1+, and bromine is from Br, 1-. So the compound that forms between sodium and bromine is just NaBr. And how I know that is that if the charges are identical, then you only need one of each. The ratio is just going to be 1 to 1. You can also do the cross-down method, And in that method, it's the one for the charge for the sodium is how many bromines you need, and 1 bromine is how many sodiums you need. We never write it as Na1Br1. Writing a 1 is redundant. There's never a use to write a 1 as a subscript, ever. If it's just 1 sodium, you just write Na. That's all you got to do. For calcium chloride, on the table, calcium is in group 2, and chlorine is in group 1. So we need to form a compound that's made of calcium. Calcium is Ca2+, and chlorine is Cl1-. If calcium has a charge of 2, chlorine has a charge of 1, in order for it to be balanced, we're going to need 2 chlorines for every calcium. But the other method is the cross-down method. If we got 2 is the charge for calcium, we're going to need 2 chlorines. And if 1 is the charge for chlorine, we're going to need just 1 calcium. So the formula just comes out to be CaCl2. 2 chlorines each with a charge of 1-, along with 1 calcium with a charge of 2+, gets us a neutral compound. For magnesium sulfide, you got magnesium with a charge of 2 and sulfur with a charge of 2, but they each have a charge +2 and -2. Magnesium is 2+, and the sulfide is from sulfur, that's 2-. Because each of them has a charge of 2, you only need 1 of each to have a neutral compound. But if you want to do it with that cross-down method, this is one where you got to be careful, because magnesium has a charge of 2, it looks like there'd be 2 sulfurs, and because sulfur has a charge of 2, it looks like there'd be magnesium would have a charge, or you need 2 magnesiums. So you might be tempted to write Mg2S2, except that's not really correct, because we want to have the lowest ratio, and the lowest ratio of 2 to 2 is just 1 to 1. So magnesium sulfide is just Mgs. Because each of them has the same charge, you only need 1 of each. Aluminum oxide, I think was in, yeah, that was an example earlier. But, ooh, I lost my mouse. Here we go. So aluminum oxide, we've got aluminum, which is in group 13, or group 13 on the periodic table. It has an atomic, or has atomic number 13, but has a charge as a cation of 3+, and oxygen has a charge as an anion of 2-. So we have aluminum, which is 3+, and oxide is from oxygen. Oops, I don't mean to write that there. Oxygen has a charge of 2-. So 2-. In order to have a neutral compound, you're going to have the least common multiple of 2 and 3, which is 6, as a charge for each of the ions. But this one, the smart way to do it is with that cross-down method. If the charge for aluminum is 3, you're going to have 3 oxygen. If the charge for oxygen is 2, you're going to have to have 2 aluminums. So the formula comes out to be Al2O3. All right, I'm not going to pull the periodic table down for the rest. But lithium on the periodic table has a charge of 1+. Phosphide comes from phosphorus. And phosphorus on the periodic table has a charge of 3-. Oop, I mean to write P. P 3-. So lithium is in the first column of the periodic table. It's an alkali metal. And phosphorus is in the nitrogen group with a charge of 3-. In order for this compound to be neutral, you're going to have 3 lithiums for every 1 phosphorus. Or with the cross-down method, this 3 goes with the lithium, so it's Li3P. So 3 lithiums, each with a charge of 1+, would have a total charge of 3+, and then the 1 phosphorus with a charge of 3- gives you a total charge of 3-. So you have 3+ and 3-, it's just Li3P. Cesium nitride. Cesium is in the first group, and nitride is from nitrogen. That's N3-. They're the same groups on the periodic table, so it turns out because lithium and cesium are in the same column, and because phosphorus and nitrogen are on the same column, the ratios are exactly the same, CS3N. Potassium iodide. Potassium is in the first column of the periodic table. Its symbol is K, so it's K+. And iodine is in group 17. So its charge is 1 minus. So you have potassium with a charge of 1 plus, and then iodine with a charge of 1 minus. They each have a charge of 1. The charges are the same, even if you do the crosstown method. It just comes out to be Ki. Same thing about writing I's. You don't want to write an I as just a capital I like this, because it could be confused with a lowercase l. And there are some cases where if you write an I as just a vertical line, it could be confused with the letter L. Then you get into trouble. So for instance, chlorine is actually an example of that. If you write chlorine like this, so it's Cl, that vertical line is just an L. If you were to write this, Ci, that's carbon and iodine, and there's no confusion. In this case, it could be carbon and iodine, where this could be confused with a capital I. So the letter L, just always make it as a vertical line if it's a lowercase l. If it's a capital L, make it like this. But capital I, always make it with the bars on the top and the bottom, so it's never confused with an L. So this is the correct way to do it. Barium fluoride. Barium is in the second group of the periodic table. It's Ba2+. Fluorine is in group 1. It's F1 minus. With that cross-down method, you're going to need 2 fluorines for every 1 barium. So it's BaF2. Let's see, rubidium nitride. So rubidium is element Rb. That's in the first group of the periodic table, Rb1+. And nitride is from nitrogen. That's N3 minus. So it's going to be Rb3N. And barium oxide. We had barium just again a little bit before. Barium is 2+, and oxygen is O. Oops, didn't mean to write that. O2 minus. So because the charges are the same, you only need 1 of each. It's just BaO. So all of the correct answers here, that's sodium bromide, calcium chloride, magnesium sulfide, aluminum oxide, lithium phosphide, cesium nitride, barium fluoride, rubidium nitride, and barium oxide. They all end with ides. The names and the symbols always have the metal or the cation listed first on the left-hand side. So those are good examples to go by. That's all you got to do. Now, when it comes to naming them, it's actually just a little bit easier, I guess you could say. The numbers don't make any bit of difference with naming the compounds for ionic compounds. The numbers do make a difference whenever you have covalent compounds, but that's also a way to tell them apart. For instance, like a compound that forms between carbon and oxygen that's covalent, CO, is called carbon monoxide, and the mono in the monoxide means there's only one. Or CO2 is called carbon dioxide, and the di refers to 2. But those mono and di prefixes, those are related to covalent compounds. So what you'll see is that for covalent compounds, we use like prefixes like mono with oxide, so carbon monoxide or carbon dioxide. Those number prefixes are keys to understanding whether they're ionic or covalent. For ionic compounds, those number prefixes don't exist. It's super easy. All you got to do is look on the periodic table. The first name is just whatever the element is. So K is just potassium, Mg is magnesium, Al on the periodic table is, got ahead of myself, is aluminum, Ca is calcium, Na is sodium, Li is lithium, Ba is barium, Cs is cesium, Sr is strontium, Na is sodium. The first half of an ionic compound's name from the cation is just the name of that element. You don't do anything to it. It's just that simple. The second half, that's the part where you have to change the name to end with ide. And sometimes it's easy and obvious, but mostly you get used to it just from hearing them and seeing them a lot. So O is from oxygen. And because the elements all end with different parts, you have to figure out where the ide ends up. And it turns out that for oxygen, only the OX goes with the ide. So potassium, it's called potassium oxide. But you've probably heard the element name with oxide in different references before. So it's not like oxygenide or oxygide or oxyide, it's just oxide. Magnesium iodide, so that's from the element iodine. You got to figure out where the ide ends up, and it turns out that instead of iodine, it's iodide. So the iode is preserved, and then it's iodide. For chlorine, you're going to see a pattern form here. For chlorine, the chlor is preserved. You put the ide at the end. For bromine, there's this brom, B-R-O-M, and that's preserved, and you add the ide to that. For sodium and nitrogen, so this is nitrogen. You got to figure out where does the ide go. So it's not nitrogenide, it's not nitrogide, it's just nitride. So the NITR is preserved, and it's nitride. Fluorine, oops, wrong color. The fluor is preserved, and it just becomes fluoride. Oops. FLU. Still early in the morning. There we go. People commonly misspell fluorine, thinking it's like F-L-O-U-R, but it's F-L-U-O-R. Barium, and then this is phosphorus. So when you write phosphorus, the phos pH is preserved, and it's phosphide. This is sulfur. Sulf is preserved, and it's sulfide. This is fluoride again, which we already used up here. And then chlorine, we already used that, chloride. So depending upon the ends of the names, you can find that it's easy. Let's see. So some of these elements, iodine, chlorine, bromine, and fluorine, all four of those happen to be halogens. They're all from group 17 on the periodic table. They all, as anions, have a charge of 1-. They all end with ene, or ine. They all end with ine. So you take the ine off and put IDE. So instead of iodine, it's iodide. Chlorine is chloride. Bromine is bromide. Fluorine is fluoride. The other elements, it's a little trickier. You might just have to memorize them, or just know them just by using it over and over. Oxygen changes to oxide. Nitrogen changes to nitride. Phosphorus changes to phosphide. And sulfur changes to sulfide. Okay, so those were good examples of naming and writing formulas for ionic compounds. And you need to practice doing that. So again, this will all be recorded. That was the nomenclature practice worksheet. If we would have been in class, I would have just handed it to you, and we would have done those as in-class examples. So this writing and naming ionic compounds, you could save it in your OneDrive and work on it in there, or you can just write it in your notebook. This is another example of writing names and formulas for compounds. So like you can predict charges for them, what's the formula for barium bromide, and then write formulas for compounds containing each of those pairs of atoms. So with aluminum and sulfur, with that cross-down method, it'd be aluminum sulfide, it'd be Al2S3, and so on and so forth. Then there are some examples here where there are names of compounds where you can write the formula. So calcium chloride is like Ca2+, and chlorine is Cl1-, so it'd be CaCl2. And all these names of compounds all end with "ide" because they all happen to be ionic compounds. So that's the method for writing and naming formulas for ionic compounds. There's not a specific homework like for tonight or for today or whatever, but once we do some with polyatomic ions, because these are all monatomic ions, I'll show you what polyatomic ions are tomorrow, and then we'll do some with the transition metals, because we didn't do any with metals that are in the D block from the scandium through zinc group. Once we do some of those, then there'll be like a self-checking homework assignment. It's related to writing names and formulas for ionic compounds. All right, so let's see. Yeah, there's like 7 minutes left. That's not a whole lot of time. But what you should do is practice the writing and naming ionic compounds problems, and that'll be good. Okay, so let's see. Stop share. All right, so let's see. Aubrey, I'm trouble getting in the room. Always reversed like those two. Xander, will they always be reversed like those two? I guess maybe what you're talking about is like how the charge from one is the same as the number for the other. And yes, that's true. So like if that cation's got a charge of 2 and the anion's got a charge of 1, you're gonna need 1 cation and 2 anions. The only thing you gotta remember is if the charges are 2 for each, that you reduce them to be like 1 each. That's how it always goes. And that's not, that isn't like a man-made thing. That's the way nature behaves. When we find sodium and chloride ions chilling together to make sodium chloride, it's always a 1-to-1 ratio. But when we find calcium ions and chloride ions together, it's always a 2-to-1 ratio. There's always 2 chlorines for every 1 calcium. That's the way it goes 100% of the time. Okay, any other questions? You can put them in the chat, or you can turn on your mic. Mics should be able to work. All right, if you don't have any other questions, work on those problems, and we'll see you back here tomorrow. If you want to stay and ask a question or put it in the chat, that's cool too. Deuces.